Good morning, dear students. This is our chapter 4 again, the second part. Chapter 4 was talking about the continuous random variables and their distributions. We started the chapter by 3 points. If you remember, we will see them in the next slide when we start our new part. We started by defining what is a continuous random variable, and if you remember, it was the variable that is defined in an interval like time, age, weight, height, prices, and so on. Then we started defining the dynasty function, the function that we integrate under in order to get any calculation for a required probability. Then also we are done with the third part in the previous slides, which is the cumulative distribution function, or the CDF, the capital F, the big curly bracket. Now, this is our second part in chapter 4 here. So this is part 2, as you see before us, and we'll start the new 3 points, which, as you will see, expectation and variance, moments and moment generating functions. Now we will start the first point in our part 2, which is the expectation and variance. As you see here, this is our new point, how we can calculate the expectation and variance for a continuous random variable. As you remember from the previous part, part 1, which we already did in the previous class, we put this table to indicate for you the differences between the continuous and the discrete case. And we are in this point now, the point that we need to get the expectation or variance. As you see before you here, that in the continuous case, your expectation will be the integration over the whole values of y. You multiply y by the probability of y, which is the density function that it will be given to you, and you integrate to get the expectation. If we need a variance, all what we have to do, you remember that the variance is two pieces. The first piece is the expectation of y squared. So all what you have to do the same thing here, but to square the y, so y squared f of y dy, and you integrate, minus mu square, which we already will be calculating it as the mu here. So let's proceed to some of the definitions and properties of the expectation and variance. Now, here again, we can see that the expectation for a continuous random variable is just an integration over the whole range of y. Here we put it generally from minus infinity to plus infinity, but whenever you get a problem, you will get what is the starting point of your y and what is the end of your y. In each different problem, it will be different. Anyway, you integrate over the whole range of y's, y multiplied by the density of y dy. And there is an important note, as you remember here, this is the one, if you need to get an expectation of any function of y, as you see here, expectation of g of y, any function of y, do you remember expectation of Hassan, which we talked about in class? So you integrate the function which was inside your bracket here, but you still gonna multiply by the density function which is given to you dy. So whatever you need to get the expectation for, you integrate over this, multiply by f of y dy to get your expectation. Your density function f of y will not change in each problem. I will give you a density function, use it for whatever expectation you need to do. This is again a reminder of the formula of the variance. if we need to calculate a variance for a random variable y, all what we have to do by definition, it's the expected value of y squared. This one we have to calculate it like y, how we calculate the expectation of y, but instead of y f of y, it's y squared f of y. Then we subtract the expected value all square, all the mu all square. If you remember also, we said that if we took the root of the variance, it will be what we call the standard deviation, which is the same measure of dispersion or variation, but this one you can put a unit of measurement. So if you calculate the standard deviation for cost or something, you can say pounds or dollars. But for the variance, since we square the whatever we are talking about, you cannot put whatever money or years or meters or something like this. So the standard deviation, again, is just the root of the variance. Now, this is a reminder again of the properties for the expectation. If we have the constant, the expectation of a constant is the same constant. Then if you multiplied your each y by a value a and then you add up to all of them b, it's like your expectation can be like this. You get the multiplication out and you multiply by the expected value of y, then you plus the b. It's like easily you drag the expectation inside the bracket, the a, since it's a constant, it will be out, then you get the expectation of y, you plug it here, then you calculate the whole thing, a mu or expectation of y plus b. Also, we said that if you have the summation of two functions, whatever it was, a summation or a minus, even if we put here in the equation a minus, you still can do it as it is. Get the expectation of the first part separately, plus or minus as you have in your original requirement, the expectation, or minus the second function which he gave to you. We remember also similar properties or characteristics for the variance. If you still remember it, I'm writing it here again, that the variance of any constant a is 0. So the variance of 5 is 0, the variance of negative half is 0, and so on. Then if we have a constant multiplied by a variable like here, we multiplied a by y, you get the a square out, then you multiply by the variance of y. Last one, if you have like an equation and we need the variance for, so you have a constant like a multiplied by y, then you have a plus or minus another constant. So the first one has to come out because it's beside y, it has to come out square multiplied by the variance of y, but the b will be plus 0 because it's a constant and the variation of a constant is 0 here. So these are important properties because I can get you a problem here, and as you will see in our examples, to get a variance for a whole equation, a number multiplied by y plus or a minus another number, and you have the information about the variation of y. This is our first example concerning the expected value and variance, and even as you see in requirement number 3, you need the expected value and variance for a specific function in y here, which is x equal this one, as you saw in the previous properties. But let's start one by one. He gave us a dynasty function here, which is, as you see before you, this is the cy squared multiplied by 1 minus y, and your y works from 0 to 1. So this is your range of integration, whatever or whenever you need the integration for. And we need the value of c here as a first requirement. All what you have to do to integrate the f of y, the density function, and to equate the integration with 0 as we did in the previous part number 1. Here, as you see in our solution, you can see that we are integrating the density function and equating the integration by 1. Here, we did the integration because we did this one integration before, as you have to multiply the y inside the bracket first, then you integrate each part. For example, when you multiply the y square by 1, it will be y square. Then when you integrate it, it will be y cube, as you see here, and so on. When you multiply the y square by y, it will be y cube. Then when you integrate it, it will be y power 4 over 4. Then you substitute by 1 minus you substitute by 0, you get this answer equated with 1, so you get your C equal to 12. This finish requirement number 1, which we need to calculate the constant. Second requirement, we need to calculate the expected value and variance. So let's concentrate how we calculate again the expectation. In order to calculate the expectation of y, you need to calculate the integration over the whole range of y, whatever it is, y multiplied by the probability of y or the density of y dy. So here my range is 0 and 1, as you see over the integration. We multiplied y by the density given to you in the above problem. Then we integrate as before, and we substitute. One time we put y equal 1, minus we substitute in all places, all y is equal to 0. We get the expectation of y as 3 over 5. Now we need to get the variance, as you will see in the next slide. Now we need to complete our second requirement by calculating, as you see here, the variance of y. So we need to calculate the expected value of y square, as you see here, because the variance includes two parts. The first part is the expectation of y square minus mu square. And we already calculated mu, so we'll square it later on. Our mu in the previous slide, it was 3 over 5. Now we need to calculate the integration over y square multiplied by the density of y dy, which is, as you see here, we multiplied y by the density of y dy. The integration, as usual, now you are good in doing these types of simple integrations. It will give you 2 over 5. This is our expectation of y square. And here is our variance, as simple as this. You put the expectation of y square minus the mu square, which is the 2 over 5 we got in the expectation square from here. Minus the mu, which was 3 over 5. When you square it, it will give you 9 over 25. So finally, your variance will be 1 over 25. In order to finish the problem, we need to get the expectation in number 3. We need to get expectation of x. And you see here, our x is defined to be 2y plus 3. So if you need the expectation of your x, it means that you need the expectation of the whole bracket you have, which is 2y plus 3. So we drag the expectation inside, you get the 2 out, then the expectation of y here plus 3. And we already have the expectation of y as 3 over 5 from the previous one. So 2 multiplied by 3 over 5, it will give you 6 over 5. Then you plus the 3 here, you get 21 over 5. In order to get the variance of x, look again at this equation again. So you need to get the variance of the 2y first, because the variance of the 3 is already 0. So the variance of the 2y, the 2 will come out as 4 because it's a 2 square, as the rules of variance say. You square the constant, then you multiply by the variance of y. If you remember, the variance of y here, it's 1 over 25 as you see here. So 4 multiplied by 1 over 25, it will give you the variance which is 4 over 25. So the problems, as you see, are very easy, are just application of an integration if you know the rule for expectation or variance, or how to include an expectation for an equation. Here is another example for the calculation of expectation and variance for the variable in hand, and also for a relation. So if you see here in the first requirement, we need the mean, which is the expectation, and the variance for y, and then also we have the expectation and variance for a relation in y. So this is like the previous problem we had before, just the previous example. We can get the expectation of y when we try to solve number one. The expectation of y is just you multiply y by the probability of y. So y, if you multiplied here by 2y, it will give you the 2y square, and then you integrate according to the limits of your y from 0 to 1. You get the answer for the mean or for the expectation as 2 over 3. We also need for the variance the expectation of y square. So you multiply y square by the same function here. You get 2y cubed as in here, and then you integrate to get an answer as half. Now we can get the variance to be calculated to finish number one. It's the expectation of your y square, which you obtained here. You put it here, and then minus the mu, which we got it above, you square it. We got 1 over 18 as the variance. This finish requirement number one. If we need to get an expectation for a relation like the one in number two, we have our x here equal 20y plus 60. So we'll have to drag the expectation for the 200y plus 60. So we drag the expectation inside this one separately and inside this one separately. As you see here, the 200 came out, and our expectation for y is 2 over 3 minus 60. So you get the expectation of the whole x as this. If you need the variance for x, so remember the 200 will come out square, multiply by the variance you obtain just the step up above as 1 over 18. So calculate this, you get this number as the variance for the x, which is a relation of y. So this is a simple problem like the one we solved before, but somehow it's like an application. Now, these are two exercises you can try to calculate like the one we did in the previous two examples, and the solutions are here. These are the solutions which are marked or inside the red rectangles, so that you can check your answer if you are solving okay, or there is something which is not clear for you. Now we are done with the calculation of expectation and variance, or even if you ask me for the standard deviation, I will take the root for the variance I obtain. And now we arrive to the second point of our part two, which is the moments. If you remember the moments, it means the expectation, whatever for y or y minus something, it depends we are defining it as row moments or central moments, as you will see in our next slide to understand the difference between both. Now, this is the first type of moments, which we call it non-central one or row moments, which is the moments we always calculate like in the expectation or variance. So we need to know that if you need the expectation of y with any power, all what I have to do to get the integration for this y with a power, multiply by the density function dy and integrate, I will get this what we called, generally speaking, since it's y power r, we call it the rth moment. So if it's power 1, we call it the first moment. If it's power 2, we call it the second moment. It's supposed to be the first non-central moment. This is the second non-central moment, and so on. Even if it's power 3, it will be the third non-central moment, or sometimes for simplicity we call it row moments. Here is what we call the central moment, which means that you are not getting the expectation of y with a power, the expectation of y minus the center of your data, or the center of y, which is mu with a power. So the only difference in this part is that you need not to put the integration for y power r, no, y minus the center power r. This is why we call it central moment. If it's power r, we call it the earth central moment, not the earth row moment or non-central moment. And as you remember also, we calculated some of these, like if you remember the variance, the variance here was the second central moment. This is our variance. The first central moment is 0, remember this? And the 0 central moment is 1. These things you can be asked for as MCQ or as if it's correct or wrong. So please, you have to remember these. The first central moment, which we call it the 0 central moment, I mean, is 1. The first central moment or mu1 central, it's 0. The second central moment, which we call it sigma square or variance, it's the variance here. So please remember these. If I get you something like these as MCQ or correct or wrong, you remember what does it mean or what does it equal. In this example, as you can read for the wording above, all what I care about here for solution is that he gave me a density function and he gave me also the range for y. Then he put a relation which is a cost as a function of y. So C equal a function in y and y squared. So as you see, your C is a constant, then something like 20y 4y squared. So it's a function of y. And then he asked for the expectation of C and the variance of C. Expectation of C, as you can remember, we can just drag the expectation inside the C relation here as like this. So if we need the expectation of C, all what we have to do to drag the expectation inside the given relation here, so that the 10, the expectation of a constant, it will be the constant itself, 20y, it will be 20 expectation of y, and 4 expectation of y squared. And here, so it will be 10, 20 multiplied by, you need to get the expectation of your y. And you remember the expectation of y, you have to go back to your function here and multiply this by y and integrate from 0 to 1. So it will give you 1/3 as here. And also, in order to get the expectation of y squared like here, you need to multiply this function again by y squared and multiply the y squared one time by one time by y, and integrate these, then substitute 1 minus you substitute 0, you get this answer here. And finally, when you calculate, you get the expectation of C as 52/3. If we need to get the variance or the variation for C, which is our second requirement in this problem, we need to get the expectation of C squared minus the expectation of C, which we already obtained as 52/3. We put it here and we square it. But we need the first part, which is the expectation of C squared. So let us substitute what is C squared and work for the squaring of this. So your C squared, it was 10 plus 20y plus 4y squared. We need to square this bracket, then drag or distribute the expectation inside. If you square a bracket, you need to multiply this whole bracket by itself. So put this bracket and the same bracket beside it, and you multiply each term by all the other terms. So we get all these terms like here, and we put the expectation for each part. So we have an expectation for 100, which is 10 by 10. We have an expectation for this one, which came to be 20 multiplied by, we have here 4 or whatever it will be, 400, then expectation of y, then the expectation of y squared, expectation of y cubed, expectation of y power 4. For sure, we have the expectation of y. We already have it from the beginning, as you see in the first requirement, as 1/3. The expectation of y squared, we use it above here when we did the variance. So we have it, the expectation of y squared, we already calculated this one in the above requirement when we got the variance. We need the expectation of y cubed and the expectation of y cubed as we did earlier. All what you have to do to multiply the original function I gave you as f of y by y cubed, then integrate from 0 to 1. So you get a final answer after you substitute by 1 minus substituting by 0 as 1/10. Also, if you need the expectation of y power 4, you multiply y power 4 by the bracket, which is the density function, to 1 minus y. So then you integrate and substitute by 1 minus substitute by 0. You get 1/15. Hence, you can get the variance of y as the expectation of C squared, which we obtained earlier in the variance, minus this one which we obtained here under the variance, and the expectation of C, the whole thing square, we already have it in the beginning. You can just square it, so you will have a final answer as this one. Now this is the third and the last part we have in part 2, which is the moment generating function for the continuous random variable, or what we called MGF. We will see how to calculate this one. If you remember the definition of this one, it was E, as I am writing here very slowly, the expectation of E to the Ty. You remember this one, which we said that you have at least to remember the definition in order to be able to get it. And in order to get the E of ETY, now we are in a continuous case, we have to integrate ETY multiplied by the given this density, which I will give you, the density probability density function, which will be given in the problem, and then get the answer for that, as we will see in the next slides. So as we said, this is just again to be sure that you understood the last part we said in the previous slide. This is how we obtain the moment generating function by just multiplying the ETY multiplied by the density dy, then you integrate your y from the beginning up to the end. I put it here generally from minus infinity to plus infinity, but for you, you may have to see what is the range of your variable. And these are some important notes. Also, it may be given to you in a form of correct or wrong or false or true or something like MCQ. Remember, if we get you something like the moment generating function, if you replace t with a zero, so you have it's either you remember it or put t equals 0 in the definition of here the mt of y, put the t equals 0, you get the expectation of e to the power 0, and since e to the power 0 is 1 and the expectation of 1 is 1, so the answer here is 1. I can get you this one again as MCQ question or as if it's true or false statement. So please be careful. You should remember also the usefulness of the moment generating function. We said that if you differentiate the moment generating function r number of times, you get the expectation, and you put t equal to 0, you get the expected value y power r. Here there is a missing r, so you differentiate with respect to t r times. So if we differentiate once, we get expectation of y power 1. If we differentiate twice, and for sure we put t equal to 0 after differentiation, we get the expectation of y squared, and so on. So this is, for example, the first one. If you differentiate only once, then you put t equal to 0, you get the expected value like y power 1. If you differentiate twice, here again, there is a missing 2. You're supposed to write here 2 to be sure that you differentiate it twice. Then you put in the differentiation, after the differentiation t equals 0, you get expectation of y squared, and so on. So this is the useful properties for the moment generating function. You can also look at these important properties. So property number 1, if you have an MGF for the variable in hand, which is y, called my of t. I will give you a moment generating function, whatever it looks like, and then I will ask you to get a moment generating function for a new variable, which is the same variable y you have plus a constant, call it a. So for example, I can give you x equal, so here we have x equal y, for example, to see it reality or real, y plus 5. So if I add up to each y the constant 5, how my original MGF, which I gave you in the wording of the problem, will be changed. It will be changed like this. You put exactly the same one I give you in the problem, multiply it by e to the constant which I gave you added to the y multiplied by t. All what you have to do, just write like this. So for example, in this one, all what I have to do to write my MGF multiplied by e to the 5t. So I will say it's e to the 5t multiplied by the my of t. I'm writing very hardly because I'm trying to write with the pen. So please look at it. This is the my of t, which is originally I gave it to you. This is t and here is y. So you get the original my of t, or the moment generating function I gave you originally above, and you multiply it by e to the 5t. Suppose I multiplied each value y by a number. So your x now is not the values of y plus 5, no. It's supposed to be I multiplied each value by 5. So I have now the y multiplied by 5 and I called it x. So what is the new MGF here for the 5 multiplied by y? It's the same original MGF I gave you, but you replace each t inside your function by 5t. So here I can do it like I did the previous one. I will do it like this. I will get the my of t, but instead of t, I will replace each t by 5t. So this is how you change the original function I give you for the moment generating function. If I multiply y by 5, you multiply each t by 5. Remember, in the previous one, we did not do like this because I added to each value y5. It happens that you write the same MGF but you multiply by e to the power 5t. Suppose I did both, so I added to each value y the number a and I divided all the numbers by p. So what you have, you will get e multiplied the t by the number I gave you a divided by the number I gave you b, and inside your original MGF given in the original function, you put each t as t over p. This will do it for the x if your x is equal to y plus a over b. This is an example, and in this example, he gave me the dynasty function or the probability dynasty function as the function you see before you as f of y equal e to the y, and your variable y works less than 0. So it means that your variable works from minus infinity. The minimum point for your variable y is minus infinity. Your y is greater than minus infinity and less than the 0 point. Okay, so this is the integration range we will do if we need, as we will see, to integrate. Now he asks us to get the moment generating function for the variable y. The news that he asked, find the three moments like expected value of y power 1, expected value y power 2, expected value y power 3. And these, you know, we can get it by differentiating once, then we put t equal to 0, differentiate another one, then we put t equal to 0, and so on. So let me just start by doing the MGF or MT of y. As here, you see that MT of y by definition is the e t e power ty. We integrate from minus infinity to 0 ety multiplied by the density function dy. Our integration will be 1 over t plus y, because as a hint for you, if you like, we have e power ty multiplied by e power y. So we can add up the powers because it's two have the same base. So e power t y, I am writing e power ty plus, we add up the two powers, plus y, and if you take the y as a common factor, you will end up with 1e like this, and your power, if you take y as a common factor, it will be y multiplied by a bracket that has t plus 1 as here. And then when you integrate, all what you have to do, write the same function as it is, then divide by the power you have, which is this one, t plus 1. And as you see, this power came us to be the answer as here. So you get the function as it is, divided by t plus 1, then you substitute 0. And anyway, the substitution or the lower bound, which we are not supposed to say substitute minus infinity, but loosely speaking, simply speaking, if you substitute in the power y equal minus infinity, this e to the power minus infinity will give you 0. So you will have this answer only, which is 1 over t plus 1. I can write this answer nicely before we differentiate, because the answer as 1 over t plus 1 can be written here as like this. It's a bracket with t plus 1. And instead of writing it as a fraction, I will write it as a bracket with a power. So it's a bracket with a power negative 1, because this t plus 1, it was in our denominator. Now, if we need to differentiate this MGF, I can differentiate it easily, like what you see here, to get the expectation of y power 1, the differentiation, put the power down, which is negative 1, the whole bracket power negative 2. Then when you put t equal to 0, you get the value, put t equal to 0 here, you get the whole bracket as 1, so you get an answer of negative 1. Take the same differentiation above, which is negative 1, the whole bracket power negative 2, and differentiate it again here. You put the negative 2 multiplied by the negative 1, so you get 2 multiplied by the whole bracket with the power negative 2 minus another 1, so it will be power negative 3. Put t equal to 0, so you get 2, because if you put again t equal to 0 here, you get 1 power negative 3, which is 1. Again, do the differentiation for the third time by taking the differentiation from above and differentiate it again. You get the power, which is negative 3 multiplied by 2. So you get negative 6 multiplied by the whole bracket, and you minus another 1 from the power, you get minus 4. Then put t equal to 0. You get here as an answer for the third moment, negative 6. So this one finished requirement number 1. If we need to get the variance, it is just an application for the relation which we know from before as here. This is requirement number 2. The variance of y is the expectation of y squared minus the expectation or the mu of y power 2, and we have these two. The first term is our second differentiation, which is 2. We got it in the first requirement. And the mu, it was negative 1. We square it, it will be 1. So 2 minus 1, it will give you a variance as 1. If we need, as you see here in our requirement number 3 in the same problem here, read requirement number 3, you can see here that he is requiring the expectation of e to the power 3y over 2. So this is like a confusing one, but if you look at it, it's not confusing. In the moment generating function, look down again. I will move you from here to here and compare the difference. What is the difference between the requirement in number 3 and the first requirement we got, which is expectation of ety. It's like he replaced the t by 3 over 2 because the y is still the y as it is. All the difference is that t is 3 over 2. So all what you have to do, get the moment generating function which is here and replace the t by 3 over 2. So we got the mgf, which is the bracket power negative 1, and we replace the t by 3 over 2 t. So this is what we got. Look, we replace this bracket, replacing the t by 3 over 2t, and still plus 1 power negative 1. So this is how we do it. We replace the t by 3 over 2t because all what he did here, he replaced the y by 3 over 2. So the expectation of this one is you replace the t by 3 over 2, and finally you replace the t by 1 because your number 3 equation, it does not have any t. So eventually your answer will be as here. It will be the bracket, and we replace the t by 1 because there was no t in my expectation of e to the 3y over 2. So we put 3 over 2 here plus 1, and then all these power negative 1, whatever this one, if you get it by the calculation or by the calculator will be, you don't have to worry about that. The idea again is that the third requirement is the same like number 1, the one we solved, but you see by comparison, by inspection, instead of t, he put 3 over 2 beside y. So in our answer in the first one, which was 1 over t plus 1, or a bracket power negative 1, we replace the t by 3 over 2 as we did here. Then we plus 1 power negative 1, and we get an answer for that. This is another example that I can give you a ready-made moment generating function. This way it has a form like this way, 3t plus 8t squared. Then I need you to work with x, which is like I multiplied the y by 1 over 3, because if you look at it carefully, this is like I said it's 1 over 3 like this multiplied by the y. This is the same like the one you have above it. So if I multiplied my original y, which is originally in my problem, by a number, this number supposed to affect every t here in your original MGF, as we'll see here. So look, if I need to get the new moment generating function for the new variable x, which is I multiplied the y by 1/3, it will affect each t. So look here, by comparison, I replace each t in the original function by t over 3 because it's like you multiply each t by 1 over 3 multiplied by t. And this is the eventually the calculation after, like you cancel 3 with the 3 here and so on, and you square and so on. But for the second one, if we need the MGF for z, which we did two things, I multiplied the y by 2, so this also, this 2 will appear multiplied by each t in the original equation here, and u plus 5 as you see here for each 2y. So this one will be separately appear as a multiplication of t outside the original function you have. So you get e to the 5t outside, but the original function I gave you in the above problem, you replace each t by 2t because I multiplied each y by 2, then you can calculate what's the brackets will be to get the power as this one, or leave it as it is if you like. The simplification is not that big. You can simplify using your calculator. This here is an exercise for the two problems we solved in the previous two examples. You have your density function as e to the minus y minus 1, and you have your y works from minus 1 up to infinity. Remember, this function, I can write it in another way, which is easy way. I can write the f of x as the following one, because it's like the power, I can divide it into two powers. I can write the power as e to the minus y, like this, multiplied by another power. You always remember that I write the multiplication as a star, multiplied by another power, which is e to the power negative 1. So it's easier this way because e to the power negative 1 is just a constant. You can, even if you like to get it using your calculator, it will be a number. So you can keep it outside the integration sign, because you can put it, if it's a number, you can put it here and only do the integration for e to the minus y and put this one as a number before the integration. And here we ask again for the moment generating function, you apply the rule, differentiate once, get the expectation, differentiate twice and apply the formula to get a variance. Then you may also find the capital F of y if you remember the big curly brackets which we integrate, but we have to do the big curly brackets first. We have a value less than the first value, which is here negative 1, as you see it. I'm referring to it by my arrow, and the value in the middle between y between negative 1 and infinity, and there is no value over infinity anyway. Infinity is like you are going to the end of your right direction without a limit. So you will have two pieces for your capital F. It's either before your y less than negative 1 or your y between negative 1 and infinity, and try to find the capital F of y as we did before. If you have a problem, you either send me or send to the TA or ask the TA by the group she sent to you in order to know how to solve this exercise. Okay, and these are the answers written in a form of the red rectangles you have, so that you can pick your answer and see how did you do in solving this problem. Now, as you see, this is just the last slide, which says that we already here in the second part finished the 3 points which we worked in this part. In the early class, which we did the first 3 parts in a separate class and separate PowerPoint. So now we are done with this whole set of the continuous random variables and their probability distribution. I hope that you can get the information, and if you have any questions, please send me an email or send to the TA to communicate and be able to understand the information. Keep safe and healthy, and enjoy the, if I can say that, enjoy the online teaching.